So good day. For today, we will discuss lesson 4.4 or the adjustment of horizontal surveys, which is previously we already discussed the trilateration method. So for today, we will discuss the triangulation. Okay, so we apply least squares adjustment or approximations using the triangulation data. So when we say triangulation, it involves angular measurements. So the expected outcomes for this lesson is to adjust the triangulation data using methods of least squares. So basically, in triangulation, so we usually measure angles instead of distances, right? Okay, so we have a conventional method of identifying positions of distant points, given that we have a known baseline. Okay, so contents for the lesson. So first we will discuss about triangulation, then the adjustment of triangulation, adjustment by indirect observations, azimuth observation equation, linearization of azimuth observation equation, and we have also angle observation equation. Then we will show you the adjustment or the example of this adjustment. For example, we are given triangulation data. So triangulation, it is a method of horizontal control extension in which angle measurements are the basic operations or observations rather. So in trilateration, we are focused on, or we are just measuring distances. But before the trilateration, we have this triangulation which is widely used because we just measure the angles instead of distances. So it influence surveyors or engineers to observe longer distance by just observing the angles. But since it involves angles, so it must have a geometrical figure. If we have this figure, then we can solve for its other unknowns such as points, sides, and etc. Given that this figure has a known side or baseline, then this triangulation can be expanded or can be densified also, given that the main triangulation is correct or contain less error. So positions of widely spaced points are then computed based on these angles, and only a minimum number of measured distances are called baselines. So therefore, for example, we have this triangulation network. This is common before the satellite system, before the advent of electronic distance meter or EDM, they employ triangulation method. So before, we have already these instruments that can measure angles, so they apply it here. So for example, you have your baseline here and you have another baseline here. So this is where we refer or start, then this is where we end. So usually this is used for checking. So if we have this baseline, so most likely these 2 points or control points are already known, then you can already determine this one by certain computations. We have this triangulation adjustment, And basically, we must consider the strength of figure, right? So that's the common practice. So the system consists of a series of joint or overlapping triangles in which an occasional line is measured and the balance of the sides are calculated from angles measured at the vertices of the triangles. So for the triangulation system, each measured baseline, which is measured with great care since its error will propagate throughout the triangulation net. So going back, they carefully measure this baseline. Why? If this line contains large value of error, tendency that error will be propagating throughout your measurement. The tendency, these points will be questionable or maybe not usable because your reference or your baseline is already erroneous. So they carefully measure this one. So that's the hard part of conducting triangulation. So the lines of a triangulation system form a network that ties together all the triangulation stations at the vertices of the triangles. Okay. So in the adjustment of triangulation, so assuming all systematic errors in the measurement of angles and distances are corrected, the observed data can be considered randomly distributed so that the method of least squares is the most appropriate procedure for the adjustments. So from your previous courses, this is already mentioned that we have this type of adjustment. So if you can remember in your, let's say in general surveying, we have this compass rule, transit rule, different methods. And the last one is we have this least squares. So least squares technique would provide the most rigorous statistical calculations. And it would provide important statistics for the evaluation for the quality of the measurements and adjusted positions of the stations, such as standard deviations and the propagated covariance matrix. So you can also evaluate your adjustments prior to your adjustment and after the adjustment, given that the error is acceptable at that point. So given that you already adjust the data or your triangulation system, then check the statistics, then this will tell you if how good or how bad the results are. If ever that some of your observations were erroneous, then probably it would suffer your adjustment, the results per se. Okay. So approximate methods for adjustments are not recommended. Okay. So when you say approximate, you just assume that I will apply 2 seconds here, 3 seconds here, or 5 minutes here. It must be based on the statistics and based on least squares in general. So least squares triangulation adjustment may be performed by condition equation, direction observation equations, or angle observation equations. Okay. So let's move on to the adjustment by indirect observations. Again, it requires linearized form. So when I say linearized, so we linearize the equation. So it is understandably that most of the equations in surveying are in nonlinear form. Like we have the distance formula, it's a nonlinear. We have this angular computation, it's nonlinear. So the distance condition for each measure distance and angle condition equation for each measure angle. So for distance, we already discussed this one in trilateration. So we develop an equation for the distance condition equation. Now we will move to the angle condition equation. So these equations would contain observations and unknown parameters. So the usual unknown parameters is the or both the coordinates x and y in general. So it requires approximate coordinates for unknown points. So usually you are given initial data, then we can solve for the position, right? So for example, you have 2 points here and you have your unknown here. Given that you already knew this line, then you can compute for the internal or interior parts of this figure, then you can solve for this position. However, your determination of this position could be influenced based on this line. How much more if you have another line that observing this line also? How much more like this, like this? So you need to consider this one also. That's why by least squares, in determining this position, we consider all of the observations at once. I mean to say, if we just this one, it will affect the other observation. Okay. But in before the least squares operation, we need to determine first the approximate coordinates, right? So you can use any of this figure or figures. So the output consists of adjusted measurements and adjusted x and y coordinates for all stations of unknown position. So let's look into the azimuth observation equation. So azimuth, for the purpose of this lesson, we refer our azimuth from the north. Though we, in practice here in the Philippines, we are more lean to the south side of our meridian. But for this exercise or for this lecture, for this course in general, we will refer our azimuth from north. So from north, okay? So that's clear. So we have this parametric form. So for your azimuth I to j, so when we say I, that is your instrument or occupied station. What else? Occupied starting point, start. And for subscript j or station j, that is your observe station or point. And instrument. Yeah. Okay. So hopefully we are clear about that. Then we have your alpha, which is your angle from north. No? Or your alpha is just your bearing. Right? Then plus C is the what we call the addition. No? So, or when you say addition, that is the constant, no? Given that, or it depends where your alpha lies. If it's in the northwest, okay? So for example, this one, it's in the northwest. Oh, no, northeast. Sorry, apologies. Northeast. So your C is 0. Therefore, your azimuth is your bearing. So if your bearing is southeast, okay? Southeast, okay? This is 1, this is 2. Quadrant. Maybe it confuses the designation of quadrant. But anyways, we'll refer to the figure. So southeast. So we add 180. But your alpha or your bearing is negative. Okay? Then therefore, the resulting azimuth is less than 180. So your azimuth is this one. Okay? So to make it clear. Then for southwest, So your alpha is positive. So that's why it's positive, because it's in clockwise direction. So your alpha plus 180, it should be greater than 180. Okay? But but less than 270 degrees. And if your angle is, or the line lies in northwest quadrant, therefore your alpha or the bearing is negative, then you add 360. So alpha plus 360, it would be equals to negative, not negative, but less than 360. Okay? So kindly remember this one. Okay, this one. So therefore, if you program this one using spreadsheet or what else? Spreadsheet? Yeah, spreadsheet or programming software, you make sure to check first the sign of your differences in coordinates to determine the sign of your alpha. Then from that, it should determine which C you will be using for that to get the right azimuth. Okay? So this requires programming skills and programming knowledge. You need to identify, okay, it's like a conditional, right? So what's the condition? So for example, you need to check the differences in x coordinates and y coordinates. So once you identify that one, you can program that one. You can identify which quadrant. Then you will know which value of C you will be using and the sign of your alpha or bearing to get the correct azimuth. Okay? So let's move on to the linearization of the azimuth observation equation. So we have this form. Okay. Right? Diba? Okay, for example, this one. Okay. So you have your azimuth. So you have differences in x, then you have differences in y. So to solve for your azimuth, so it is equals to tangent x minus x sub o, then y over y sub o. Tangent, let's say azimuth. So azimuth now is equals to arctangent x. Okay, so which results this one? So we have C here. For that, we can convert this acute angle, because we need to convert this angle into a azimuth, no? And your azimuth also a residual. Okay, that's why we have this standard equation. So looking to the here, now looking back here, so it's a nonlinear equation. So it's nonlinear. So let's put from this equation, then we have this function. No, we can substitute this equation into this function. Okay. So we have this function x sub I, y sub I, x sub j, and y sub j. So let's draw the figure to make this clear. So we have j, we have I. So for each component, or for each point, we have x sub I, then y sub I. Then we have x sub j and y sub j. Okay? So these two coordinates dictates the angle of your line, no, referred to a meridian. So we substitute this, or we equate this equation to this one, to this function. Then from this function, we have this one, okay? So we just add this function. So since this is a nonlinear, so we use the first order Taylor series of approximation to linearize the equation. So here we have the equation, the function, then is equals to f or function of x sub I, y sub I, x sub j, and y sub j not, okay? Mean to say, we compare this one to the using by this approximate. So these are the approximate because of this subscript not, okay? Plus the partial derivative of the function with respect to x sub I, y sub I, x sub j, and y sub j, okay? So determining the partial derivatives of your function, so let's say first derivative of your arctangent, okay, is equals to this one. So we apply these properties to the next part of the equation. Then we have here, okay. So it clearly shows that these are the solution. Then we proceed here. Okay, so take note, ij here, ij squared is equals to the squared of x sub j minus x sub I plus squared of quantity y sub j, y sub I. So this is your distance formula, right, of a line. So that's your distance formula. Then we already arrived with this equation. So this is for the partial derivative of your function with respect to x sub I, okay? But remember, this is just the example. So when you work with your problem, you need to at least try to derive, okay? So applying the same process we have for with respect to y sub I, x sub j, and y sub j, okay? So obtaining after the partial derivatives of this one, we now substitute those to the equation. Now we arrive with this one, okay? So we have not, and not is equals to k. So k here is your observed azimuth minus the approximate azimuth angle. So it's the same with distance, right? You have your observed distance, your k, let's say k of length, k of a line, observed distance minus the approximate distance. So it's the same process, right? So approximate distance, okay? So now let's proceed to angle observation equation. So we will derive last from the previous slides, we are just concerned with a line, okay, line and its angle. How about if we have two lines, then therefore we have an angle in general. So let's consider point B as your backside station, point I, it's your occupied station, or this is where our instrument placed. And we have your point F, which is the foresight station. So each of these two lines, or if each of these lines has its azimuth, right? So AZ sub IF for the foresight and azimuth IB for the backside. And keep in mind this angle, or let's say theta, contains residuals also. No, we anticipate that there are some residuals in our observation, or let's say residuals when we adjust, right? So going back to the figure, so we have this angle observation equation. Okay. So now we have your backside, and we have your foresight, then instrument. Okay. Now, your angle BIF, or let's say theta, is equals to azimuth sub IF, the minus azimuth, or A sub IB, which is equals to their, we have this equation. And D here is the difference between their constants. So as previously defined, right? So generally, this equation is equals to angle BIF plus the residual. Okay? So again, since this is a nonlinear function, then we need to linearize this form, right? So we have this function of x sub b, y sub b, x sub I, y sub I, x sub f, and y sub f. So this coordinates are the coordinates of the points that we are considering. So this is for your backside, coordinates of the instruments or instrument, and coordinates of your foresight, which is equals to angle BIF, which is this one, and your residual, okay, this one. Then we equate this one to this formula or equation as previously defined here. So when we linearize, again, using the first order Taylor series of approximation, then, okay, we have this one plus the partial derivatives of the function with respect to this coordinates, x sub b, y sub b, x sub I, y sub I, then x sub f, then y sub f. Okay. Now, developing the observation equation, after we determine its partial derivatives, as previously shown before, as what we have derived, no? So we have this output, no? So kindly check the observation equation. So always keep in mind to, if you cannot memorize the observation equation, then it's either you memorize or derive the equation. But if you able to memorize, then good for you. So please take note with this subscript. No, this is y sub I minus y sub f over if squared, not. Okay. Keep in mind, this is not. Okay. So we say not, therefore the, this distance, given that if these two coordinates are not controlled, therefore your distance IF is varying. Okay. So same with the previous example we did in previous meeting or previous lesson. Then, okay, XF. So when you say F, you already knew what is F. Okay, let's try to write it down. B is your backside station. I is your foresight. Oh, no. Instrument. Station. Then F is your foresight station. Okay. Plus, so kindly see the formula properly. Okay. So we will observe that this side of the equation, the left-hand side of the equation, are full of knots. Okay. Meaning to say, you need to compute this in every iteration. Okay. Which is equals to K plus your residual. So K here is the observed angle minus your computed or the approximate angle. No? Okay. So angle BIF naught is equals to this equation. So it's not okay. So, but if you ever see a subscript of not, no, therefore it's changing. The coordinates are changing based on the current approximation or current data that you input. Okay. So I think that's it. So now let's proceed to the adjustment of intersection. So operation of the determining the position of an unknown point using horizontal angle observations from two or more controls. So most of the adjustments consist of multiple stations. Then this multiple station consists of many observations. Okay, so let's look with this example later. Okay. Okay. So for the adjustment of intersection, it has a unique solution. So it requires a minimum of two angles. So each additional angular observation contributes a redundancy. So what does it mean? Okay, intersection, like such as this one. Okay, this point here in question. So at least you have two angles, and considering you have your baseline here, you can compute for this position. If you have another baseline here and you observe the same point, then you have a redundant measurement. How much more you have another one, you have another redundant measurement, no? So given that this redundant measurements contains less error or good observation, it will help improve the determination of this position using the least squares adjustment, no? Because in least squares adjustment, usually we have this redundancy, no? We observe this point multiple times, but how can we determine its most probable value? So we can do it by least squares. So for each observed angle, azimuth observation equation should be set up, which in turn becomes an input to subsequent angle observation equations. Okay, so let's have an example of intersection problem. So given that we have three unweighted horizontal angles, so they have equal weights, were observed from control stations R, S, and T. So let's compute for the least square adjusted coordinates of station U. Okay, so we have for angle 1, angle 2, angle 3, and angle 4. Then the control station, we have for RST. So when we say control, they are already fixed in nature. So most likely, so for example, we took a backside at station U, then we took a foresight at station S. Basically, let's view this formula. Okay, so the observation equation. Most likely, okay, but let me write the angle for example. That is angle URS. URS. Station U is unknown. Station R is known. And station S is known. Okay? So if you look with this one, station U is your backside. Station R is your instrument. And station S is your foresight. Given that we have this situation and we apply this to your observation equation, some of this equation can be can be reduced, or this equation can be reduced because for known stations, the correction for its coordinates are not required, or it is just equals to 0. So for station S, that is F, so we can somehow make it 0, then 0. So for station R, it is a known position and instrument, then we can make this 0. So we just simplify the equation. 0. So only the backside station left. Okay? But if, for example, all of your backside, foresight, and the instruments are unknown, then we use the full observation equation. Okay? Hope that is clear. So let's proceed to the example. So first step is to determine the initial approximation for the coordinates of station U. So again, minimum of 2 angles is enough to determine the unknown station, or let's say station U. Okay, so for example, you have points A and B as control, then you have your angles here observed, then you can determine this position. So using the coordinates of station R and S, the distance RS is computed as this one, okay, based on the given one. So from the coordinates of station R and S, the azimuth of the line between R and S is determined using equation, this one. Then the initial azimuth of line RU is computed by subtracting theta 1 from the azimuth of line RS. Okay. Then, after that, using the sine law, or law of sines, using triangle RUS, an initial length of, or for RU naught can be calculated using this equation or sine law, right? So we have your distance. So are you not? So where is are you not? So this one, are you not? Okay. So this distance. Then from once you already have your, for example, you have already your azimuth of this line, then you can compute for this position approximately. So what's the purpose of determining this position in the early stage of this solution? So this helps the adjustment to have at least small amount of corrections because you already approximate the value based on your observations. Okay, but if your other observations are erroneous, it will lead your approximate value to be adjusted uh, abnormally, which leads to wrong answer. So once you already have the components of U naught, okay, or let's say components of the line, no, the latitude and the departure. So this is your departure and this is your latitude, right? Then you will arrive with a coordinates of the point. Basically, if we are not up to the redundant observation, this data is already the answer. Okay? But again, it doesn't help us to know how good the observation because we don't have yet statistical output based on the adjusted and the determined quantities. Okay? Continuing, we also perform the same process for the other lines. Okay? To have initial distance. So next is to formulate linearized equations. And again, take note that coordinates of control stations, as stated lately, are held fixed during the adjustment. So their change in coordinates, or let's say the correction of their coordinates, are just equals to 0. So in using the prototype angle observation equation, stations should be assigned to their proper designation. So where is the backside, where's the instrument, and where's the foresight? Okay. So for angle 1, B, I, F are replaced with U, R, and S respectively. So we have here your table, right? To guide you, which is for example, for angle 1, which is the backside station, which is the instrument station, and the foresight station. Okay, so if I'm looking at this figure, dy dx or dx dy are 0, 0, 0, 0, dx dy, dx dy, this is 0, 0, 0, 0, dx and dy. So that's why we already reduce our equation to this one. So kindly refer to our angle observation equation. Then we have this one, right? So that's it. Make sure you arrange the matrix properly. So now we already formulate the linearized equation. So for you not to be confused, you can create your table to identify for this angle, which is the backside, which is the foresight, and which is the instrument. So to determine your backside, you have this guide, which is the arrow. So if we have the arrow here, or the arrow pointing or touching the line, that's your foresight line. And the other part or other side is just the backside line. Okay, hope it is clear. Then You next evaluate the pertinent matrices. So if we have the J matrix, okay. So keep in mind we have this row. That is the um, number of seconds. Let me check the value of rho. So it's 206,264.8062 seconds. Okay. So yeah, that's it. So from this, we have your J matrix here. Okay. Then for your K matrix, you have this one. Okay. Then after that, you perform the matrix solution. Then you have your first correction of your coordinates. Then you apply that correction from your first estimate or first approximation. Then you will have your new coordinates of x sub u and y sub u. Then once you still have this size of corrections, you repeat the process. Then we go back to, let's say, first part. We go back. So when you compute R naught, RU naught, SU naught, so you have new values of your X and Y of station U. No? So that's why for the next iteration, you have different value of this one. Then you have another different values here, here. So this whole matrix changes now. So keep in mind to check the angles always. So for example, you need to identify the correct C for each iteration, because if you use a software, let's say spreadsheet software to compute, you do not just rely on the equation. You need to check always the condition. For that, you will arrive the correct value of C. Diba, we have the C0, or it could be 180, 180, or 360. Okay. Then you repeat the process until negligible corrections occur. So for example, you have already corrections of 0.00001 feet. So probably that is too small. That is already acceptable based on the precision given or required. Then that's your final answer. Then after that, compute for the post-adjustment statistics. Okay, like this one. Then this is your statistics for, let's say, angle 1, angle 2, angle 3, and angle 4. So V, 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 V. So those are the residuals. Then also compute for the reference standard deviation. Okay. So M here, take note, M is the number of observations. How many observations we did? We did 4 angle observations. Then how many unknowns? That is your N. So that is to have a degree of freedom of your standard deviation. Okay. Therefore, the reference standard deviation is plus or minus 8.8 seconds. Then from that, we have your covariance matrix. You get the uh, you get the elements, diagonal elements to determine for your coordinate x. So you have this one, and for y, you have this one. Okay, so to determine the error in the position of station U, it is given by this equation. Then you have your standard deviation of this station. Okay. So this ends our lesson.